Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video here, we're going to be exploring effusion, and you're wondering what is effusion and how is effusion important in determining how various particles behave when there is a form of leakage in the system. So in this particular video, we're going to be exploring rate of effusion, and based on this we're going to design a system where first we are going to borrow from what we know about the Graham's law of effusion, and from Graham's law of effusion, which I'm going to abbreviate as GLE, we actually consider, or he considers, that the rate of effusion, which I'm going to abbreviate as that, is indirectly proportional or inversely proportional to the square root of that particular particle's molecular mass or molar mass. And therefore, one question is this: why is this relationship this particular way? The reason why is because of the mean speed of the particles, and the mean speed of the particle is indirectly proportional or inversely proportional to the square root of the molecular weight or the molar mass of the same particle. And so therefore we can lead to the conclusion that in terms of effusion, when a specific particle leaves a system either due to puncture or leakage, this rate of effusion is actually related to the rate at which the particles hit the area or specific area, which we are going to abbreviate as a knot. And so this is as well going to be inversely proportional to the square root of the molecular weight. And so once you have these conditions taking place, you're asking yourself this question: how are we going to create a goal that will be able to determine the specific relationship, which means deriving a formula that actually determines the rate of effusion? And so based on our goal is to use the rate of our specific collision, which is represented as RZ, and this rate of collision between particles and the surface is going to be linking us to the rate of effusion. And effusion, in terms of the definition, is going to be linked as well to finally effusion of our system. So in this video we are going to go through these steps one by one, and all that, as a result of that, derive our formula. So first off, let's create a system that we know of. And creating a system means that when you have a system that is a form of a vacuum, and in this vacuum we have this particular space that particles are trapped, exerting pressure on this particular surface, and all these particles here, they are moving in the same direction, heading towards this wall, which has an area which is represented as A, and based on our coordinates, don't forget that this is our X and this is our Y. So what if you have a specific part that is an opening, and this opening here, we are going to consider the opening's area to be represented as A naught, and this actually leads to something quite interesting, because in this case we know that all particles are moving in the X direction based on the velocity. And so at a specific temperature and pressure, we are able to consider really deep into what is happening in the specific area where there is a leak, and this actually leads to the separating of the gas from the vacuum. And so in this part, when you look in detail by zooming in, we see that as the particles leave this particular system, which is going to represent as green going in to outward, this rate by which our molecules escape is equal escape is equal to when you have this system actually sealed and you have the particles hitting against this region. So therefore, once the particles are hitting that system, we can actually go in and show that there is an equal relationship between the molecules escaping and when the molecules hit the area that is specifically the whole area without creating the hole. So in this part, we're going to now dive really deep into the solution to our derivation method. And so in this part, we know that the collision flux is going to be linking us to the collision rate, so the rate of collision. And so based on our first step, we are going to start off with a collision flux, which is represented as Z subscript W, and based on our previous video is equal to our specific collision frequency divided by the area multiplied by the rate, which is the time interval. And this is equal to the pressure all over. In here we have the square root of 2 pi multiplied by the mass, and then you have our K, which is the Boltzmann constant, multiplied by temperature. So take note that we need to multiply both sides by the area. And so by multiplying both sides by the area, we have our new expression where we have our area cancelling out here, and what we're left with is the collision frequency divided by time, and this is equal to, take note that P is multiplied by the area, and this is all divided by r square root pi m, our Boltzmann constant, and temperature. So this here is leading us to our second equation, and based on our second equation, we need to now note that this is actually going to lead us to the relationship between the area of the whole space, which will experience the same pressure as the area of this particular hole right here. That is our target where we're going to create that particular hole. So before the hole is created, the pressure of this whole system is equal to the pressure that is exerted on our potential hole. So therefore, as a result, expressing this in terms of our hole, we are going to link our area now to become a knot. So therefore, our new expression will now be Z, which is the collision frequency over the change in time, is equal to collision flux multiplied by the area, specifically the hole, or you can just introduce it as A. I will erase that. Let's just make it O0, not. And this is equal to pressure multiplied by the specific area of the hole, and this is all divided by 2 pi mkt. So this actually leads us to our next step, which is having our conditions where we can change our K, which is shown right here, to an R. And so changing our K to an R, we need to note that based on our specific assumptions, which includes the following, we know that where our R, which is our gas constant, is equal to the number of particles multiplied by our Boltzmann constant, and we know that the molecular weight is equal to the mass multiplied by our specific number of particles. We can solve for K here, and on the other side here we're going to solve for our mass. And so by so doing, we are able to get our K as the subject of the formula here, which is now equal to our gas constant over the number of particles, while on this other side we have our mass to be equal to the molecular weight divided by the number of particles. So by putting these two equations in this orange equation right here, specifically looking at the K, we can then create our new expression for this, where we are going to put these two in equation. Let's make this one. So this is our equation 1, and therefore we are going to get our new expression where we are going to first off make this to be equal to P multiplied by our specific area of the whole to be equal divided by the square root of, first we have 2 pi. Take note that our m is in this case expressed as big M, which is the molecular weight divided by the number of particles. And so once we have this, big M multiplied by divided by the number of particles, and we know that our K, which is shown above here, which is equal to R over NA, is going to be replaced as well. So we have our R over NA, and this, take note, is multiplied by the temperature. And so therefore, looking at this, we know that NA times NA is NA squared, and so the square root cancels out our NA squared, and we're left with is NA, and the NA is going to be at the top, which is the numerator, and as a result of that, we have our new expression for our specific rate of effusion, which is equal to P A naught, which in this case is the pressure multiplied by the area of the hole, and this is multiplied by the NA, which is the number of particles, all over. Take note that we have the square root, and we have 2 pi multiplied by m, which is the molecular weight of our particle, multiplied by our gas constant, and multiplied by our temperature. So we have now 3 possible expressions to play around with in this particular case right here. And it's quite interesting to see that there is another expression that will lead us to determining the mass change. And relating the mass change involves the following. When you're losing that many particles due to effusion, how is this related to the mass of the overall system before the release and the new mass of the particle after, or the system after is actually released at a specific time? And so that relationship is where we have our next part, which connects the Cook-Stens method, which actually shows relationship with our temperature, no, with our mass and our time. And so therefore, where we have the pressure vapor to be constant. And what do I mean constant? It means that in this case, when we have a specific cell, which are going to represent as this, and either this part here is a solid, a hot one, or a liquid, and in this part here we have a system that has pressure, that is vapor pressure, acting everywhere around the top region. When take note that this is really hot, we can assume that when you create a hole, in this case a little small hole right there, we can come to the conclusion that the pressure of the vapor, or vapor pressure, is going to be equal around as well to the pressure that is released when the particles are leaving the system in their gaseous state. Therefore, in this particular case, we can assume that based on this change in the constant pressure of vapor pressure, we will then assume that the mass before, which is represented as m1, and the mass after the release of that number of particles is accounted for based on the change in time and the number of particles in here that are released, which is expressed as change in m. Therefore, since we have this, we know that the rate of effusion is constant. And so once the rate of effusion is constant, we will lead to our connection with our mass in terms of our change in m, which I'm going to bring right down. Change in m is equal to the specific rate of effusion, which is ZW, multiplied by the area of the hole that is created. That will lead to our rate of effusion, and this is multiplied by the mass of that one particle atom multiplied by the change in time. And so this is where we will be able to associate what we know of as ZW and connect it really well to the overall big picture of the rate of effusion. And so once you have this, take note that solving for ZW in this particular expression, we have our change in the mass divided by the area of the hole multiplied by the mass of that one atom, and this is multiplied by the change in time. Therefore, since we know that where the collision flux based on our previous expression that we derived is equal to the product of the pressure and the number of particles, all divided by the square root of 2 pi. Take note that we have our big M, which is a molecular weight, multiplied by the gas constant, multiplied by the temperature. We are going to put this in this equation, and we are going to have our new expression to be now in terms of our pressure. And so our pressure multiplied by the number of particles, all divided by the square root of 2 pi molecular weight times the gas constant multiplied by temperature is equal to the mass difference multiplied or divided by the area of the hole multiplied by the mass of that one particle multiplied by our change in time. And so once we have this expression created, our next goal is to, what we're going to do? We are going to change a couple of things in here, where we're going to change our specific NA, which is the number of particles. And so we know that where the number or the molecular weight is equal to the mass multiplied by the number of particles, we can then rearrange our expression in here to be now in terms of the pressure and only the mass and the mass and also the molecular mass, not the number of particles. And therefore in here, once you rearrange this, where we have our pressure when you solve in here to be equal to the square root of 2 pi mRT multiplied by the change in the mass all over the NA, which we know to be the number of particles, and this is multiplied by the area of the hole multiplied by the mass and the change in time. We would then introduce this into this equation, and what we're going to have is our new expression, which is in the intermediate phase to be pressure to be equal to square root of 2 pi RT, and this is multiplied by, take note that we have m, which is a molecular mass, to the power of 1 over 2 minus 1, multiplied now by the change in the mass, all divided by the area naught, which is the area of the hole, multiplied by our change in time. And so the final step is to evaluate our power, and as well this power, which is what we see right here, and what we have as a result is we have m to the power of negative 1 over 2, and that will be incorporated into the square root. And so our final expression will be in terms of pressure to be equal to the square root all of 2 pi RT all over the molecular mass or molecular weight, and this is all multiplied by the change in the mass, all divided by our area of the hole multiplied by the change in time. And so this is really important when you're dealing with the vapor pressure or determining the vapor pressure of either a liquid or a solid atom. So on our next video, we're going to apply this particular solution for our vapor pressure to a specific example, and based on that we will be able to recognize various derivation steps and looking for the key step that will be important in applying it to our specific example in our next video. So thanks for following me through this particular video. Hope you're able to understand how vapor pressure works and how this is actually crucial when connecting the effusion rate and also that of our understanding of the connection between the collision flux and the rate of collision. So thanks for following me through this. Truly appreciate it. Hit the comment down below. Let me hear your thoughts. By that way I can talk to you all soon. Stay smart as always and believe in yourselves.